Hello everyone, welcome to this lecture. So, in this lecture we will see the a more efficient solution for the degree reduction problem due to Gennaro-Rabin-Rabin. This is called as the GRR degree reduction method, and we will also see an example to get a better understanding of the degree reduction method. So, just to quickly recap, this was the BGW reduction method that we had seen in the previous lecture, right, which is done in 2 stages, right. So, let me write down the 2 stages here. So, when you go again, so there is a typo here, I should have used a different variable S1, S2, Si and Sn here. So, in stage 1 we do the randomization, and in stage 2 we do the degree reduction. Okay. The randomization is done by adding shares of 0, random shares of 0 lying on a 2t degree polynomial, and then the degree reduction of that random share of the 2t random sharing, 2t degree random sharing to t degree random sharing happens via truncate operation. Now, what the GRR degree reduction method does is the following: it cleverly combines both these 2 stages in a single stage. Namely, in the same stage it will be doing the randomization plus the degree reduction, and that is why it is more efficient, right. Because if we follow this BGW reduction, then we have to do the interaction both in stage 1 as well as in stage 2, but if we can combine both those 2 stages in a single stage, then the parties need to interact only once, they do not need to interact twice, and that will be saving both in the number of rounds as well as the amount of communication which is needed. Okay, so, let me explain the GRR degree reduction method again. This will require t to be less than n over 2. Okay. And as I said earlier, this is a necessary condition not only with respect to the GRR degree reduction method. Later on we will prove formally that any generic MPC protocol, if you want through that, if you want to evaluate securely a multiplication gate, we need this necessary condition of t less than n over 2. Okay. So, in stage to begin with, the parties will first compute a non-random vector of shares of AB lying on a 2t degree polynomial. How they can do that? Just locally multiplying their respective shares of A and B. No communication has happened at this point. Now, the idea is that since t is less than n over 2, that means I can say that n is greater than equal to 2t plus 1, okay, and the degree of k polynomial is 2t, and we have more than 2t plus 1 number of shareholders or 2t plus 1 number of shares of this k polynomial available. By the way, I will interchangeably use the term shares of the polynomial or the shares of the value, both mean the same thing. Shares of the value mean distinct points on the sharing polynomial. When I say shares of the polynomial, by that I also again mean the distinct evaluations of that sharing polynomial. Okay. So, the first thing to observe here is that the constant term of this k polynomial, which is the unknown value a b, is a linear function of this k values k1, k2, ki, kn. This is because if you recall the Lagrange interpolation, we know that alpha 1 k1, alpha 2, so we know that alpha 1 k1, alpha 2 k2, alpha I ki and alpha n kn, they together interpolate uniquely this k is a polynomial. Why uniquely? Because n is greater than equal to 2t plus 1 and the degree of k polynomial is 2t. Okay. And we know the form of k polynomial. K polynomial can be expressed as a in terms of the distinct points on the k polynomials in terms of the delta polynomials. Okay. And if this is the case, then by substituting z equal to 0, I obtain the following relationship. I can say that k of 0 is the delta 1 0 times k 1, delta 2 0 times k 2, delta n 0 times k n. So, now let me call this delta 1 0 to be the constant C 1, delta 2 0 to be the constant C 2 and delta n 0 to be the constant C n. They are basically your Lagrange interpolation coefficients which we had discussed when we discussed Lagrange polynomial interpolation over the finite fields. Okay. And k of 0 is this AB. Okay. So, the summary here is that unknown AB. Why unknown AB? Because it is secret shared right now through the k polynomial. No one knows the value of A times B, because A was secret shared, B was secret shared and parties have just locally multiplied their respective shares of the A and B. So, what we have summarized here is that based on Lagrange interpolation, we know that this unknown AB A times B is a publicly known linear combination of unknown values k 1, k 2, k n. Why publicly known? Because the Lagrange coefficients fancy C 1, fancy C 2 and this fancy C n, they are publicly known. They have got absolutely nothing to do with your k 1, k 2, k n. Okay, because this C 1 is delta 1 0 and delta 1 polynomial is basically publicly known. Delta 2 polynomial is publicly known, hence delta 2 0 is publicly known. Delta n polynomial is publicly known, hence delta n of 0 is publicly known. What is not known are the actual k 1, k 2, k n. Not known in the sense it is not publicly known. K 1 is available only with P 1, k 2 is available only with P 2, k I is available only with P I and k n is available only with P n. And we know that how to securely compute linear functions of private inputs. What does it mean here and why it is applicable here? So, we are considering right now a scenario where P 1 has the value k 1, P 2 has the value k 2, P I has the value k I and P n has the value k n. In that sense, they are private inputs of the respective parties. And we know that there is this unknown A B which can be expressed as this public linear function of this private inputs. So, if we ask the parties P 1, P 2, P I, P n to respectively secret share k 1, k 2, k I, k n, then we can apply the same linear function, the Lagrange interpolation linear function on the shares of k 1, k 2, k I and k n and end up getting shares of A B. and our goal is finally to obtain shares of AB. We do not want to make A public, we do not want to make B public in the degree reduction problem, and we do not want to make AB also public. Somehow we want to obtain shares of AB lying on a random t degree polynomial, and computing shares of AB is equivalent to computing this linear function in a secret shared fashion. And remember, we had already seen that how to securely compute linear functions in a secret shared fashion, right. That was our starting point to discuss the BGW protocol. The simpler case for the BGW protocol was when the inputs of the parties are available with the respective parties, and we want to compute securely just a linear function of that. It is very easy to compute that, and that is what is the scenario here based on this observation, and that is precisely what the GRR method does. We want to compute securely a secret sharing of AB as a publicly known linear function of secret sharing of k1 to kn. Right now the secret sharing of k1 to kn is not available, because k1 is right now not available in a secret shared fashion, it is available only with p1. k2 is not available in a secret shared fashion, it is only available with p2 and so on. But if we want to compute securely this function, that is always possible by asking the respective parties to secret share their private inputs, and the private inputs of the respective parties are now k1, k2, ki, kn. We do not want to make the values k1, k2, ki, kn public, but still we want to compute the output A times B, which is the linear combination of this k1, k2, ki, kn in a secret shared fashion, and this can be done very easily. And why it will be ensured that the final shares of AB, which are computed as linear function of secret sharing of k1, k2, ki, kn will be a random vector of shares, because that will be triggered by the randomness which is used to securely compute this linear function. Okay. So, now let us see what exactly happens in the GRR degree reduction method based on whatever we have discussed till now. So, we want to securely compute a linear function of publicly known linear function of k1, k2, ki and kn, and we know how to, and that is a linear, since it is a linear function, we know how to securely compute it. Basically each party has to secret share their private inputs, which are k1, k2, ki, kn respectively, and since the linear function is publicly known, namely the linear combiners are publicly known, the parties can apply that linear combination on the shares of k1, k2, ki, kn, and then obtain the respective shares of AB, right. So, we ask P1 to do this, namely it picks a random polynomial k1z of degree t and secret shares k1, namely it runs an instance of summit secret sharing to secret share the input k1. Similarly, P2 will be asked to execute an instance of summit secret sharing and secret share k2. Pi will be asked to act as a dealer and run an instance of summit secret sharing to share ki. So, for that it will be picking a random polynomial of degree t whose constant term is ki, and like that we will ask the nth party to pick a random polynomial of degree t with constant term being kn and distribute the shares. And after that we compute this linear function. Why we can compute this linear function now? Why it is possible? Because the inputs for this linear function, namely k1, k2, kn, is now available in a secret shared fashion, and since C1 is publicly known, each party, say the first party, it computes C1 times the first share of k1 plus C2 times the first share of k2 plus C1 times the first share of ki plus C1 times the first share of kn. Okay. Similarly, Pi it will take all the ith shares for k1, k2, ki, kn, multiply them respectively with this public constant C1, C2, Ci, Cn, and it will obtain its new share called Ci. And similarly, the nth party, it will take all the nth shares that it has got in the respective secret sharing instances, multiply them with C1, C2, Ci, Cn respectively, and obtain this share. And the claim is now that this vector of values, this vector of C values, which now the parties have collectively, with ith party having the ith component, lie on a polynomial Cz whose constant term is t, whose constant term is ab, and its degree is t, and it is a random polynomial. That means, all its coefficients except the constant coefficient are random elements. Why so? Because each of these polynomials k1, k2, ki, kn, which are picked in the individual instances of Summit secret sharing, they are random polynomials, of course, except the constant coefficients. So, k1 has all its coefficients randomly chosen except a constant coefficient, ki has all its coefficient randomly chosen, kn has all its coefficients randomly chosen, and if you take a linear combination of this random polynomials with random coefficients, you obtain a random polynomial whose coefficients will be random, of course, except the constant coefficient. And why the constant coefficient ab? Because the constant coefficient will be C1 times the constant coefficient of k1 polynomial plus C2 times the constant coefficient of the k2 polynomial plus Ci times the constant coefficient of ki polynomial plus Cn times the constant coefficient of the kn polynomial, which we know is ab, right. So, now you can see we do not have to do a two stage approach. In the single stage, just because we want to now compute this linear function, and to compute that linear function anyhow parties have to run instances of random secret sharing. We are now able to do the degree reduction as well as bring in the randomness or the randomization just in a single stage. Okay. So, let us see a demonstration here, okay. And imagine that our circuit is a simple circuit consisting of just one multiplication gate, A times P, that is what we want to compute. Our T is equal to 1. So, imagine A was secret shared through this A polynomial, B was secret shared through this B polynomial. The parties first locally multiply their respective shares of A and B, okay. But right now they are not exchanging them publicly and reconstructing the function output, because we have to first do the degree reduction, and now since after the multiplication there is no more gate, we have to publicly reconstruct the function output. That means, now our circuit is of this form: A is coming from one party, B is coming from one party, there is only one multiplication gate, and then there is a function output y. Okay. So, the parties first secret share the inputs, then they do the degree reduction here, and then they reconstruct, because there are no more gates after this multiplication. If there would have been follow up gates after this multiplication, then they would have proceeded with whatever they have obtained at after the degree reduction. Okay. And remember, we had seen in the earlier lecture that if we do not do this degree reduction and directly reconstruct y, then that leads to the breach of privacy, namely the party the corrupt party could narrow down that what could be the possible input combinations and what could not be, right, and that is a privacy breach. But now we can show that that is not going to be the case if we do the degree reduction. So, right now this shares 2, 0, 3, 1, they are not publicly reconstructed, they are your intermediate k1, k2, k3, k4, okay, lying on a 2 degree polynomial. Why 2 degree? Because t is equal to 1. So, 2 times t will be 2. So, the parties will do the degree reduction, and as part of the degree reduction we need to know the Lagrange coefficients here. Okay. So, I have worked out the Lagrange coefficients for you here. So, this is the k polynomial as per our notation, and this k polynomial is actually passing through your alpha 1 comma alpha 1 2, alpha 2 0, alpha 3 3 and alpha 4 1. So, your k polynomial passes through these 4 points. Okay. So, that means we now need the delta 1, delta 2, delta 3, delta 4 polynomials here. The delta 1 polynomial will be a 3 degree polynomial, where in the numerator you have all the alphas except alpha 1 as the root. So, alpha 1, alpha 2, alpha 3, alpha 4 in this setting we have set to 1, 2, 3, 4. So, you can see in alpha 1 polynomial in the numerator all the alphas except alpha 1 are the roots, and then to ensure that this alpha 1 polynomial evaluated at alpha 1 should survive or give the value 1, we have set the denominator like this. So, you can now see that the delta polynomial at alpha 2 and the delta polynomial 1 at alpha 3 and this delta polynomial 1 at alpha 4 will vanish, but it will survive at alpha 1. Okay. As a result, the first Lagrange coefficient will be the constant term of this delta polynomial will be 4, right. So, remember all the operations are performed over Z5, where the plus operations are addition modulo 5 and multiplication operations are multiplication modulo 5. The delta 2 polynomial in the numerator will have all the roots except alpha 2, and to ensure that it survives at alpha 2 we have the corresponding denominator. By substituting z equal to 0, we get the second Lagrange coefficient. Similarly, we obtain the third delta polynomial and correspondingly the third Lagrange coefficient, and the fourth delta polynomial and the corresponding fourth Lagrange coefficient. So, this C1, C2, C3, C4 they are publicly known. They have got nothing to do with the shares of A, B and the shares of 4 which right now are available with the parties. So, now we know that unknown C C, unknown constant C, not constant, unknown value C is a linear combination, namely it is C1 times the share 2 which is available with the party 1, second Lagrange coefficient time the value k 2 which is 0, third Lagrange coefficient time k 3 which is 3 plus C 4 times k 4 which is 1. But the value 2, 0 and 3 and 1 they are right now the private inputs of the first party, second party, third party and fourth party respectively. So, we have to compute this linear function in a secret shared fashion. So, that is what will be done now. So, party 1 will act as a dealer and he will secret share its private input k 1 through a 1 degree polynomial. Party 2 will act as a dealer and secret share its private input which is k 2 through a 1 degree polynomial. Party 3 will act as a dealer and secret share its private input namely k 3 through a 1 degree polynomial, and similarly party 4 will act as a dealer and secret shares its private input k 4 through a 1 degree polynomial. And now we have to compute this linear functions. So, k 1, k 2, k 3, k 4 they are now already available in secret shared fashion. Apply the same linear combination. So, on the respective shares of k 1, k 2, k 3, k 4. So, the parties will individually apply the Lagrange coefficients, apply the linear combination and then they will obtain the respective shares of C. So, this will be now your vector of shares of C which will be considered as the output of the degree reduction. And now in your circuit there are no more gates to be evaluated further. Okay. we are considering a function which has just one multiplication gate. So, since there are no more gates to evaluate further, the parties will stop at this point and it is now time to reconstruct the function output. So, they will make the shares of final shares of C public, and the parties will now interpolate alpha 1 0, alpha 2 1, alpha 3 2 and alpha 4 3, and now they will obtain this C polynomial. So, we will again take the case where P 3 is corrupt, right, similar to what we had done when we saw the same example to understand the challenges associated with evaluating with the process of evaluating the multiplication gates. So, I have now highlighted in bold the view of corrupt P 3. Okay. So, corrupt P 3 will have the shares of A, shares of B, and whatever shares it obtained during the degree reduction problem, and it itself will be acting as a dealer and secret sharing K 3, and then finally, it will be seeing all the shares of C being made public. So, everything which has been highlighted in bold constitute view 3. And it also knows the Lagrange coefficient because they are publicly known. So, this is the view 3, the question mark denotes they are the unknown values. So, now a malicious P 3 with unbounded computing power would like to infer that okay, the final result is 4. Is it because of the case that A is equal to 1, B equal to 4, or is it because A is equal to 2, B equal to 4, B equal to 2, or is it because A is equal to 4, B equal to 1, or is it because A equal to 3 and B equal to 3. Again, let us recall that if we do not do the degree reduction and directly evaluate it as per the BGW invariant, right, then a corrupt P 3 based on view 3 could narrow down that 2 combinations are possible, 2 input combinations are not possible. But now we have to see that after doing the degree reduction, can P 3 throw away certain A B combinations from her view or not. So, let us first try the combination A equal to 4 and B equal to 1, and again based on the previous exercises, if P 3 fixes A to be 4, then given that she has seen the share 2 for that unknown A, that freezes the A polynomial in her view. And if she freezes B equal to 1, then given that she has seen the share 4 for that unknown B, that freezes the B polynomial to 1 plus Z in her view, and that freezes also the shares that the other parties would have obtained for that unknown A and B. Then once the shares of A and B are fixed with respect to whatever hypothesis P 3 is making in her mind, that also fixes K 1, K 2, K 3, K 4. Now, if K 1 is fixed to 0, given that P 3 has seen the share 2 for that unknown K 1, together that freezes the K 1 polynomial that P 1 would have used. And if K 2 is fixed to 3, then given that P 3 has seen the share 2 for that unknown K 2 together with K 2 equal to 3 and her share being 2, that fixes the polynomial that P 2 would have used to share that K 2, and that would have fixed the other shares of K 2 as well. K 3 anyhow was shared by P 3. So, she is not going to make any hypothesis, and K 4 if it is fixed to 0, that along with the fact that for that unknown K 4 P 3 has received the share 0, that fixes the K 4 polynomial from the viewpoint of the corrupt P 3 and the other shares of K 4 that the other parties would have received. And now P 1 will check, and now the corrupt P 3 will check whether the linear combination, the Lagrange linear combination of this shares of K 1, K 2, K 3, K 4 gives you these values, and answer is yes, that is quite possible. Whereas, without degree reduction based on the view 3, corrupt P3 was able to throw away certain values of AB. In the same way we can, I am leaving it as an exercise, but we can show that the same view 3 which adversary P3 has seen by participating in the protocol will be consistent with the hypothesis A equal to 2, B equal to 2, as well as with the hypothesis A equal to 3, B equal to 3. That means, if we do the degree reduction and then finally reconstruct a circuit output, then there will not be any breach of privacy. Adversary will only learn the final outcome C equal to 4, but it cannot narrow down whether it was actually because of A equal to 1, B equal to 4, A being 2, being 2, A being 4, B being 1, or A being 3 or B being 3. All 4 possible input scenarios are equiprobable from the viewpoint of corrupt P3, and hence the privacy property is satisfied. So, with that I end this lecture. Thank you.